This shape looks as if a luminous curve has been drawn inside a circle, but the program never draws that curve. It draws hundreds of straight line segments, one after another. Their arrangement creates the curved boundary that we perceive. In this episode, we will follow the complete construction from one short rule to a reproducible SVG renderer written in C+++20. We will see how an integer index becomes an angle, how modular arithmetic chooses the other endpoint, and how two trigonometric functions turn both endpoints into pixels. Then we will separate the parameters that change the mathematical structure from those that only change its presentation. Every line of code shown here belongs to the public release tagged artifact 001 version 1.0.0. That immutable tag means you can inspect, build, and run the exact implementation used in this explanation. Begin with a circle containing n equally spaced positions numbered from 0 through n-1. For every source index I, calculate a destination multiplier times I modulo n. Then connect the source to that destination for 12 positions and multiplier 2, source 4 maps to 8. Source 7 gives 14, but 14 is outside our circle of 12 positions. Modulo 12 wraps it back to 2. No matter how large the product becomes, the result returns to the circle. At a low point count, the discrete construction is obvious. We can identify individual positions and follow individual chords. As the count grows, nearby source positions usually produce nearby destinations. The family of chords becomes dense and its boundary begins to read as a smooth envelope. The featured multiplier is 2. Its result is commonly recognized as a cardioid-like envelope. The wording matters. The output does not contain a cardioid path, it contains straight SVG lines whose collective organization suggests that form. The code also accepts a real-valued multiplier. With an integer multiplier, destinations coincide with numbered positions. With a fractional multiplier, a destination can lie between two discrete positions. Treating that value as a continuous angle lets us animate the family smoothly instead of jumping from one integer design to the next. The implementation starts by collecting every input in an option structure. The mathematical controls are the point count and multiplier. Width, height, radius, line width, opacity, and colors control the presentation. A few extra options can reveal only the first chords, highlight one mapping, or display point markers and labels for teaching. Before opening an output file, the program validates these values. There must be at least 3 points. The multiplier must be finite and non-negative. The radius must be greater than 0 and no greater than half of the shorter canvas dimension. These checks do more than improve error messages. They protect the assumptions used by the geometry that follows. The function called point-on-circle is the bridge from arithmetic to geometry. It receives an index, the number of positions, the center of the image, and a radius. Dividing the index by the count gives a fraction of one complete turn. Multiplying by 2π converts that fraction to radians. The code subtracts pi over 2 as a phase offset. In the SVG coordinate system, that places index 0 at the top of the circle instead of on its right. The offset rotates the entire composition. It does not change the relationships between chords. Cosine gives the horizontal displacement from the center and sine gives the vertical displacement. Multiply each by the radius, add the corresponding center coordinate, and the abstract index has become an SVG point. Notice that the function accepts the index as a double, not an integer. That small design choice is what allows a fractional modular destination to land at an intermediate angle during animation. The renderer creates the output directory, opens the SVG file, and computes the canvas center. Its radius is the shorter of width and height multiplied by the radius parameter. As a result, the circle remains circular on a rectangular canvas and stays inside its limiting dimension. Coordinates are written with fixed point formatting and 3 decimal places. The SVG header records its dimensions, a descriptive title, the background, and a group containing the shared line style. Now we reach the entire mathematical renderer. A loop visits each source index. The destination is calculated with fmod, multiplier times the source, modulo the number of points, for the non-negative values used by the renderer, and as long as their product remains finite, that destination stays between 0 and n. The program calls point-on-circle twice, once with the integer source and once with the possibly fractional destination. We now have 2 Cartesian endpoints. For the normal case, the renderer writes one SVG line element with x1, y1, x2, and y2. That is the key evidence behind our opening claim. There is no curve command hidden elsewhere in the main form. One mapping becomes one straight chord. If a source index matches the highlight option, its chord receives the accent color, full opacity, and triple width. Optional circles and text labels are written afterward. These overlays do not alter the algorithm, they expose it. They are useful for moving from an explanatory diagram to the dense finished piece without changing implementations. The loop performs constant work for every visible chord, so rendering time and SVG size grow linearly with the chord count. The implementation does not build an array of all points or all lines in memory. It calculates endpoints and streams each element directly to the file. It helps to divide the controls into two groups. Structural parameters change the construction. Presentation parameters change how the same construction is seen. Point count is structural. At 12 or 20 points, we see a diagram. At hundreds of points, we see accumulated density and a smoother apparent envelope. More points also mean more overlapping strokes, so point count interacts strongly with opacity and line width. The multiplier is the second structural control. Changing it reorganizes every destination and produces different families and apparent lobes. A fractional sweep makes the transformation continuous. The program still draws a complete set of straight segments in every frame. Only the destination calculation has changed. Line opacity is presentational but visually powerful. Low opacity turns the number of overlapping chords into tone. Frequently crossed regions become brighter. Line width changes the graphic weight and can overwhelm fine detail when the point count is high. Foreground and background colors alter contrast and perceived luminosity without changing a single endpoint. Radius scales the circle against the shorter canvas dimension. Width and height choose the output format and aspect ratio. These values can adapt the same geometry to square, landscape, or portrait output. Finally, the chords option reveals only the first part of the loop. Combined with highlight, point markers, and labels, it turns production code into its own explanatory instrument. That is why these controls belong in the renderer rather than in a separate hand-drawn diagram. Reproduction begins by checking out the public release tag. The project needs CMake version 3.20 or newer and the C++20 compiler. SVG generation has no graphics library dependency. The renderer writes the vector markup directly. Configure the repository, build the release executable, and run it with the featured parameters. 720 points, multiplier 2, a square canvas, radius 0.46, and a thin low opacity stroke. Parent output directories are created automatically. Because SVG is resolution independent, the result can be inspected at any zoom or rasterized later at the required delivery resolution. The algorithm uses no randomness and coordinate formatting is fixed. With the same inputs, the generated SVG is deterministic, although different SVG rasterizers can produce slightly different pixels along anti-aliased edges. The release also registers 3 focus tests. A smoke test renders 120 chords. A negative test verifies that 2 points are rejected. A construction layer test combines a partial render, a highlighted chord, markers, and labels. These are not proofs of the mathematics, but they guard the executable's main success path, an important invalid input, and the options used in the explanation. For animation, render a sequence while changing the multiplier by a small amount in each frame, then encode those frames separately. Keeping vector generation independent from the video codec makes the mathematical render simple and makes the output reusable. The complete piece rests on a compact chain of ideas. Modular multiplication chooses a destination. An angular formula places both indices on a circle. Sine and cosine produce Cartesian coordinates, and SVG records one straight line per mapping. Repetition turns that discrete rule into an apparently continuous form. The tagged code, parameter table, build commands, presets, and references are available in the public repository linked in the description. Try a low point count first, then raise it. Hold the presentation fixed while changing the multiplier, and then experiment with opacity once the structure is clear. If this kind of open, reproducible, generative artwork is useful to you, you can also support the project through the Buy Me a Coffee link. In the next episode, we will move from multiplication around a circle to the distribution of prime numbers on the Ulam spiral.